I guess there's also an example, right? That would be pasted in. So it says if there exists a staircase with n steps, you can climb up either 1, 2 steps at a time. Given n, write a function that returns the number of steps. So I guess given 1, you'd return 1. Given 2, you'd return 2. And those are the basic examples. And then when you get to something like 3, it should be a combination of all previous examples, right? Sure. So right off the bat, this seems like this problem follows some sort of dynamic programming approach, just because I would be starting from the bottom and using all previous information to get to my final solution of n. So my very first cases, I just have 1 and 2, and to get to the next point, my options for traveling to say an x plus 1 point is to either travel 1 step from the step that was directly before, or 2 steps from the step 2 before. So it seems like really I end up combining the two values, right? So the number of ways I have to get to x plus 1 is x minus 1 plus 1, or x minus 2 plus 2. So here my answer for 3 ends up being 3, because I can either take the 2 ways I got to 2 and add 1, or I can take the 2 ways I got to 1 and add 2. And continuing with 4, I should be able to go to all the ways that I get to 3, all the ways I get to 2, right? So 5, and then this continues to 8, and so on. I'm pretty sure that's how it would hold. So if I were to have n, I should just be able to repeat this all the way, right? So that I start off with my values of 1 and 2, and then I just increment. And for complexity-wise, that ends up taking O of n time complexity and O of 1 space complexity to solve this. Is it okay if I code this out?
Hold on. I have some follow-up question.
Sure.
So just to, I guess, so an example of like, if n is equal to 4, there are 5 unique ways, right?
Yeah.
Then, so I guess, yep, your logic makes sense. Then my other question is, so we can, I guess, you say this will be O of n time?
Yeah, because we're going to have to linearly go through all of the numbers, right, up to n.
The staircase?
Yeah, and there's no way we can really skip numbers, right? Because you can't, like, if our n was 10, we can't just do 7 in the middle without having 5 and 6.
Uh-huh.
Yeah.
So wouldn't that be like a Fibonacci sequence?
I'm sorry?
Fibonacci?
Our numbers?
Relationship. Like using the formula, right?
Yeah, so I think that does end up representing the Fibonacci sequence. And I know there's supposed to be an equation, but I can't recall what that is off the top of my head.
Okay, that's fine. So if we use a dynamic programming approach, you say it will be O of n time?
Yeah.
Let me think. Is that right?
Yeah, because we'd have to go through all of the numbers, right?
Huh? Right? I'm trying to think, because the solution I have is O of n times k.
N times k. What is k in that case?
K is is the how many sets, like, so I just try to generalize it. So if you can take a number step from the set k, oh, k could be, 1 step, 3 step, or 5 step.
Right. So you're saying if instead of there just being 1 or 2 steps, there would be multiple steps?
Yeah, so, I forgot to include this. So what if instead of being able to climb just 1 or 2 steps at a time, you could climb
see.
any numbers from a set of positive.
Yeah, so that definitely changes things. Because for R1, the reason it ends up being linear is because the number of step types you can take is constant, right? You can only take 1 or 2 steps. If you were able to climb some k number of steps instead, then now you have to look at all previous k numbers, right?
Right.
So then it's the exact same algorithm, except now instead of just checking 1 or 2 back, you would have to set your base case to being all of the first k elements set, and then you would look at all previous k elements, which would take n times k time, right?
Right.
So yeah, n times complexity, and it's still a constant space complexity. Well, I guess it's not constant. Now it's big O of k, space complexity.
Yeah, exactly.
Cool. So I guess should I code out this follow-up?
Yeah, that'll be the,
Okay.
yeah, sure. That sounds good.
Cool. Sure. So def and steps on the array and options. Let's just call it that. I guess I can't assume that options is sorted, so I'm going to actually just go ahead and sort it. And that ends up being relevant for the case where I actually want to make sure that I can use, when I set the initial values, I can, refer to I can set it correctly. So I guess there is a problem with this in the sense that my previous algorithm kind of breaks down because I assume that there are no gaps between all of the different steps you could take, right? Here, though, in the example, you could take multiple steps. So instead of climbing 1, 2, 3, or 5 steps, I'm only doing 1, 3, and 5, right? So what I should be able to do in that case is, as a first step, can I always assume that one of the k is always going to be 1? I'm guessing no, right?
So you can just, you're given from that set of positive integers. So you're going to assume they're a positive integer, but
Okay,
it could,
got it.
It's not zero.
Okay. So, right, this changes it up so that instead of me setting my initial base case the way I would before, it's just like, something that's hard-coded in. Instead, I would have to first, I guess, loop through and set, yeah, this actually changes a lot. Instead of it being O of k space complexity, I would want to have an O of n space complexity solution where I actually store what the number of steps are for all of the steps up to n, right? And then what I would start off as my base case setting is instead that I would set all of the values of k to equaling 1, right, inside of my, say, solutions array. And then I would start from, int equals 1 and move upward to see how many steps I could take at position n. So let's say that my solutions array is equal to 0 times n. So n is going to be the length of the array. And then, so my solutions is just 0 times n. And then I say for option in options, I want to have solutions of option -1 is set to 1. So if I were, as an example, trying to find the sixth step and I had 1 through 5, I'd have index 0, index 2, and index 4 set to 1. Because my solution is always, because there's no 0th step, when we always start from the first step, my 0th index is just treated as the first step. So now what I want to do is for step in range n, I want to go ahead and see how many ways I can possibly get to this step. And the easiest way to do that is to iterate through the options at each step. So what I can say is if step minus option is less than 1, then I break. And what this basically ends up meaning is that there is no remaining option. There is no remaining step value in my options array. Could work. There is no previous step I could have had. I may have a bug here in that it should be less than 0 instead of less than 1, but we can check on that with the test case. And I'll go on with the the main logic. So the main logic should end up being that if there is an option inside of options where I could have had a previous step, I want to make my solutions at my step plus equal solutions of step minus option. So what does that really mean? If we were to make it concrete, if I had my step as being 2 and my option was 1, I'm saying that the number of ways I can get to step 2 also includes the number of ways I got to step 1 plus 1. Well, not plus 1. I'm including that. I'm saying that I can move from step 1 to step 2. And then at the very end, I should be able to return solutions of n minus 1. So I think this ends up being the translation of my main idea into code. Let's go through this with a test case. So let's pretend that I'm checking through with 1, 3, 5.
Sure.
Options equals 1, 3, 5. And my n is going to equal 6. Or, yeah, let's say it's 7. 8, because that's a pretty good number for the values we have. I start off, I should have 0 8 times. So this is 1, 2, 3, 4, 5, 6, 7, 8. Right off the bat, I should have for each of the options in options, I'm going to set 1 minus that value to equaling 1. So I have index 0 set to 1, and then let's just copy this over. Oops. Index 0 set to 1, I have index 2 set to 1, and then I should have index 4 set to 1, right? 0, 1, 2, 3, 4. Cool. I start off with my step on line 45 being 0, and I say for option and options, the very first value I'm going to get is 1, right? So is 0 minus 1 less than 1? So there's a bug here. It should be is it less than 0? If my step minus option is less than 0, that means that there is no previous value I could have gone to get to the step, so I break. But I have, yeah, so that should be all that's required. Because that means that there is no future way that I can get to the step, because all of the other steps are greater, right? So the step minus option will be less than 0 for all of the future options as well. And so the solutions at this step never gets increased. So at index 0, that's correct. Now I get to index 1, and my first option is 1. And so here I see that step minus option, my step is 1, my option is 1. That's not less than 0. Here I have 0, so I continue. And so I end up saying that my solutions at index 1 is going to be step minus option, so that is 0. So now this gets updated to 1. I have one way to get to 2. The next time through, I have my option set to 3, and again, I'll have the same logic. I'll break out. Cool, so this seems to work out so far. Now we're at number 3, or we're at index 2. Again here, I should have the same logic. I check if the option of 1 works out. It does. This gets updated to 2, but I have no way of getting to, the previous, the next option is going to break again. So I go to the next index. Again, I check the 1. my solution here gets updated to checking the next value or the previous value of index 2. So this becomes a 2, as in 2 ways I can get to the number 3. But I'm not done, because now I get to the next option of option 3. And so I check back 3 indices, 1, 2, 3. And I see that index 0, there's also a 1 here. So again, now my value here gets updated to 3. Is this correct? Are there 3 ways for me to get to step 4? I would say so, because I could take one step. No, there isn't. Oh yeah, there is. I can take 4. I can do 1, 1, 1, 1, or I can do 1, 3, or I can do 3, 1. Those are all valid ways for me to get to the step.
Right.
I think the core logic seems to hold out, mainly because we found the one bug on line 47. The only thing that we really need to check for is that we are returning the correct solution in the end. So at each intermediate step, our solution is correct. The last thing we do is return solutions of n minus 1. Does this represent the nth step? I think following from the other logic we had, where each of the steps represent it's the end plus 1 step. So if we have the n minus 1 step, I think we will have the right solution in the end. I think this should be sufficient as a test. Is it okay if I print out and run some code as tests?
Yeah, let's do it.
Okay, so we go print some steps on options on 8. Let's just include this as a test case, just to verify that what I said is true. Oh, I put them in backwards. It should be 8 and options. I don't know what the actual number is. Wait, did I put it in backwards again? Oh, this is just supposed to be n. Oops. There was a bug, in that I assumed that I had a.
Yep.
Yeah, so I'm not entirely sure if that's correct. So maybe I'll just go with the numbers I had before. Whoops. Oh, I'm using this n value, but I'm not updating it anywhere. Okay, so there is a bug.
Yeah.
In that I seem to list index as out of range. I have option minus 1. That is wrong. Right, okay, I can see where this goes wrong. It's because my option values are much greater than the actual value. Because there's no way I can use any of the options if they're greater, right? So if option is greater than or equal to n, in that case, I should end up breaking, right? Is it equal to or less than? Yeah, I want to have 0 times n, but I want to have if option is greater than n. In that case, I would continue. Right, so getting to 3, this one's correct, and then 4, I should get 3. I do, and then 5, there should be, let's see, there should be, if I look at 5, there's one way from just taking the 5, or I can end up having 1, 1, 1, 1, 1, or 3, 1, 1, 1, 1, 3, 1, 3, 1, or 5. So 1, 2, 3, 4, 5 ways to get to 5. I think is the right way here. Yeah. There are some edge cases that you would have to handle for, say, invalid inputs, but I guess I'm allowed to assume that I have valid input on this, right?
Yeah.
Like my n will always be greater than 0 and things like that, and it's non-empty options. Okay, cool. So given that, I think this will be my solution.